then you get a shape called a catenary or catenary. So if I have like a couple telephone poles and points to hang something, oh, I lost my pens again. And that cable is going to have this nice arc. Now, at first glance, you might say, hey, that looks like a parabola, but it's not a parabola. It's called a catenary or catenary. I think I spelled that right. And it's a version of the equation e to the x plus e to the negative x over 2. And what we're missing there are the constants due to the density of the cable and the distance we're stretching it across and how long the cable is, right? So we need to know the length of the cable, the distance we're trying to span, and how dense the cable is. Once we have all that, we can get constants to go with it. The abbreviated name of this sucker right here is the hyperbolic cosine, COSH, pronounced cosh. That's the cosh function. And cosh is a relatively simple function. It's just a combination of e to the x's added up divided by 2. So let's just, for fun right now, take the derivative of the cosh. So derivative with respect to x of the cosh of x is equal to the derivative of that other stuff, e to the x plus e to the negative x divided by 2. Now, dividing by 2 is just a constant, right? So it's just going to chill out. So we're still just dividing stuff by 2. And then derivatives are nice. They move through addition relatively easily. So I just need the derivative of e to the x, which is a lovely e to the x, as we were reminded last section. And the derivative of e to the negative x would be negative e to the x. Negative x, sorry, thank you. And that function right there happens to be what we call the sinh, S-I-N-H, the hyperbolic sine. Okay, so we are now delving into a new area of mathematics called hyperbolic trigonometry. And it's remarkably crazy and beautiful that these e to the x functions have similar properties to the traditional sine and cosine. Okay. For example, we know the derivative of the cosine is the negative sine. Well, we don't have the negative, but it's the hyperbolic sine. And guess what happens if we take the derivative of the hyperbolic sine? We're going to get the hyperbolic cosine back. Yeah, and even better, what happens if we take the antiderivative or integral of the hyperbolic cosine? Well, that means we're just taking the integral of that e to the x plus e to the negative x over 2. And just like derivatives, constant multiples hang around. So we're going to still have that division by 2. Antiderivative for e to the x, e to the x. Antiderivative for e to the negative x is negative e to the x, or negative e to the negative x. And then we have that pesky plus c that hangs around because we don't have boundaries. And so the antiderivative for the hyperbolic cosine is the hyperbolic sine, or the sinh. Okay. So then people played around with these once they discovered, ooh, that's kind of weird. And it turns out there is a hyperbolic tangent and a hyperbolic cotangent and a hyperbolic cosecant and a hyperbolic secant. And they all have similar properties to the sine, cosine, tangent, secant, cosecant, and cotangent. Whew, crazy stuff. Yeah, it's weird. And there's other ways to think about them, but my favorite thing is just they are physically relevant because we see them everywhere. There's a cable or a chain hanging that's loose that gravity can pull on. Okay, just kind of wild. All right, so what else are we going to do with these suckers? Let's take a look at the hyperbolic tangent next. Oh, actually, I was going to bring up a quick graph of the hyperbolic cosine. Let's ask GeoGebra. New GeoGebra picture. And then most programs recognize COSH Calculators, I'm not sure if TI has a hyperbolic cosine. I don't think so. And just to double check that that is the same thing, if I type parentheses e raised to the x plus e raised to the negative x, and then I divide that by 2, they become one and the same function, right? So the computer recognizes the hyperbolic cosine. And so there's that hanging, yours does it? You have hyperbolics on the Casio? Yep, you do. You even have inverse hyperbolics. We'll get to those in a minute. So it depends on the utility you're using. Does Desmos know about them? Probably. It does? Cool. Oop, not Dexmos, Desmos. So fun, beautiful math. So if I type COSH of x, Desmos loves it. Nice. Okay. So let's take a look at the hyperbolic tangent. So that would be the TANH of x, pronounced the tanch. I know there's no C in there. It always threw me too. It's like, why is it? What? But tan sounds kind of weird. If it's a silent H, then it's like tangent. So somebody came up with tanch. I do not know the history of who decided to pronounce these. And just like with sine and cosine, the hyperbolic tangent would be the hyperbolic sine divided by the hyperbolic cosine. Now, I don't know about you guys, but when I get excited about math, I start writing fast, and my brain is used to writing COS x and TAN x. And so often I drop the H. If you see me do that today, say, hey, you owe me a slice of pizza. And we'll get enough slices for a pizza party in a couple of weeks. Okay. So you guys pay close attention. All right. So what is the hyperbolic sine? Well, we know the hyperbolic sine is e to the x minus e to the negative x over 2. And we know the hyperbolic cosine is e to the x plus e to the negative x over 2. And since top and bottom are divided by 2, those dividing by 2's divide out. Okay. So we can say it's more simply e to the x minus e to the negative x divided by e to the x plus e to the negative x, which is a wee bit more complicated than just the hyperbolic sine or cosine, but tangent has always been a complicated creature, right? People have rewritten this in a variety of ways. So one trick for rewriting this is to multiply top and bottom by e to the x. And sorry, I'm looking for another color here. There was color. So if I multiply the top by e to the x and the bottom by e to the x, then I'm going to get a new version here. I'm going to get, let's see, e to the x times e to the x, e to the 2x, minus e to the negative x times e to the x. Not 0, but 1. Right, because the exponents will zero out, right? So that'll be e to the 0, which is just 1. Okay. Another way to think about it is that e to the negative x is 1 over e to the x. And so when we multiply by e to the x, they give us a 1 in return. Denominator is going to be pretty similar. That's going to be e to the 2x plus 1. Okay, so that's another way to think about it. We'll come back to that in a little bit. Well, wouldn't it be fun to take the derivative of the hyperbolic tangent? So let's see, what's the derivative of the tangent? The derivative is secant squared, right? Wouldn't it be cool if the derivative of the hyperbolic tangent was the hyperbolic secant squared? Let's try it. New page. Isn't this exciting? This whole new territory of math unexplored by us. It is just different letters, yeah. It's not exactly the same. It's like an alternate dimension where things are a little bit different. Like in that dimension, I don't wear glasses and I actually have more hair, for example. It's like same but different, you know? And I actually wear a tie. That would be weird. Okay, so we want to take the derivative of the hyperbolic tangent, which we know is also the hyperbolic sine over the hyperbolic cosine. So that'd be the derivative with respect to x. Slice of pizza. All right, glad someone's paying attention. Okay, so there's one slice of pizza. All right.
So what if we catch you before you write the page?
He caught me. He caught me. Oh, no. You got to wait till after I put the x in. Okay. So, and we're going to have to use the quotient rule here. So quotient rule says take the derivative of the first function, the top function, right? So derivative of the hyperbolic sine is the hyperbolic cosine times the bottom function, cosh. And then it says minus the derivative of the bottom function, which is the sinh, times the top function. Oh, I did it twice. Okay, there's 2 more slices of pizza. If it's a 6-slice pizza, there's half a pizza. Yeah, okay, we're getting there. All right, and all of that is divided by the cosh squared. And you know what? I think people put those soundings like cosh and sinh to remind them to put the h in. Because when I say cosh, I feel compelled to put an h. All right, did I do the quotient rule correctly? I think I did. So what is this? This is the, I could say this is the cosh squared minus the sinh squared all over the cosh squared of x. And I just want to focus on the numerator for a minute. So what happens if I square the cosh? I'm going to bring up a new page. We'll come back to this one. So cosh squared, well, that would just be e to the x plus e to the negative x over 2 squared, which means I have to multiply that thing by myself. So by itself. So I'm going to pull out a 1/4 here, and then I have to take e to the x plus e to the negative x times, e to the x plus e to the negative x. And so I get some distribution. I'm going to keep the 1/4 separate. So let's see, e to the x times e to the x, that's e to the 2x. And then e to the x times e to the negative x is just a +1. Negative e to the x times e to the x is another +1. And then I'm going to get what? Plus e to the negative 2x when I multiply by e to the negative x times e to the negative x. All right, I better slow down. I'm getting too excited here. Okay, so that's not too bad. Cleaning it up just a little bit, leave the 1/4 out front because I don't feel like writing it over and over again. We've got e to the 2x plus 2 plus e to the negative 2x. Now, multiplying the sine or the sinh by itself isn't going to be too much different. So just consider squaring the sinh. The only difference, instead of a plus there, I'm going to have a minus. So I think the only difference is going to be we're still going to have a quarter. We're still going to have an e to the 2x. In the middle, we're going to have a -2. And then a negative times a negative is a plus e to the negative 2x. Oops, big parentheses. So that's one version of the cosh squared and one version of the sinh squared. And again, there are different ways to manipulate this, but I'm going to stick with this for now. And the previous equation for the derivative of the tangent said we need to take the sinh squared away from the cosh squared. Okay, so I want the blue thing minus the black thing. All right, so the 1/4 is chilling out front, agreed, because they both have it. So let's switch color. So I'm trying to take the cosh squared minus the sinh squared. And so I'm going to have a quarter times, well, I'm going to have an e to the 2x minus e to the 2x. Bye-bye. I'm going to have a 2 minus a -2, which I think is a 4. And I'm going to have an e to the negative 2x minus e to the negative 2x, which is 0. So the difference of the squares is 1. Whoa. Okay, so unlike the, so this is one place they deviate a little bit. In regular trig, it's cosine squared plus sine squared is 1. In hyperbolic trig, it's cosine squared minus sine squared is 1. Can't be perfect everywhere. So back to this page, we now know that we have 1 over the cosh squared. Well, let's see. In regular trigonometry, what's 1 over cosine? Secant. Well, in hyperbolic trigonometry, 1 over the cosine is the hyperbolic secant. So we now have the hyperbolic secant squared. Ta-da! Not amazing? It'll grow on you. Oh man, I gotta take a deep breath. That was quite the workout. All right, let's see. What other fun can we have with these guys? Did that. All right, let's see what an inverse trig function looks like. So just a reminder about regular trig. If we know y equals the sine of x, and that's f of x, then f inverse of x is often written as the sine inverse of x, which is also called the arc sine of x. So are you guys familiar with the arc expression with those inverse trig functions? And the reason it's called that is the sine function takes an angle. Well, an angle in radians is really an arc length, right? So it takes an arc length and spits out a ratio. Inverse trig functions do the opposite. They take in a ratio and spit out an angle, which is also an arc length. Hence, they're called arc functions, okay? Because they spit out angles, radian angles are arc lengths. Similarly, sometimes hyperbolic trig functions are, instead of it's being called like the cosh inverse or the sinh inverse, they're called the arc sinh or the arc cosh. And so they are popular. And sometimes people get lazy and they drop the C, so sometimes you'll see it written as AR sine or AR sinh. So let's see what, if Desmos relates, does any of those. Does it know arc cos? It does know, oh, maybe. Let's see, 1. It recognizes it. Okay, so what about arc cosh of 1 should be 0? Okay, yeah, I recognize it. Oh, the graph of it. Yeah, so just imagine this graph right here, flip y with x. Now, if we flip y with x, instead of getting a sideways looking hanging chain, we would get a horizontal one, and it wouldn't be a function. So like the parabola, you have to pick one side or another because you get a plus or minus in there. So this one starts at the point 0, 1 and heads out. This one would start at the point 1, 0 and head out, kind of like a square root function. So let's ask it to graph that for us. Okay. Can you see that as the inverse there? Okay, so similar to an inverse of a parabola is a square root function. This isn't a square root function though, but think, what's the inverse of an exponential function? Talked about this last class. Logarithm. Yeah, in this case, natural log. So it's got to have something to do with the natural log. Okay. So let's figure out what it has to do with the natural log. So we are going to go for finding, I don't know, what did I write down in my notes? It doesn't matter. I was going to do inverse cosh. So we start off by taking y equal to the hyperbolic cosine, COSH of x. And you can do one of two things, solve for x and then switch x and y, or switch x and y and then solve for y. I'm going to switch later. So I'm just going to try and solve for x. To do that, I need to rewrite this as e to the x plus e to the negative x over 2. And I got to isolate x. problem right now is I have an e to the x and I have an e to the negative x, so it's going to be a little tricky to isolate. But I'm going to at least multiply the 2 over to the other side. So let's say 2y is equal to e to the x plus e to the negative x. And remember, our goal here is to solve for x, so we can get an inverse. And now I'm going to throw in the trick I used on the hyperbolic tangent. I'm going to multiply both sides by e to the x. If I do that, I'll get 2y e to the x on that side. Over here, I'll get e to the x times e to the x, which I'm going to write as e to the x squared for a moment. I realize we could write it as e to the 2x, but just bear with me. And then if I take e to the x times e to the negative x, what do I always get? Lovely number 1. And then I'm going to bring everything to one side. So I'm going to take that 2y e to the x and subtract it over. Okay? So that means I'll have 0 on one side, and on the other side, I'm going to write them in this order: e to the x squared minus 2y e to the x plus 1. And if I do a little substitution here, like I say, hey, let's let u equal e to the x. Then this becomes 0 equals u squared minus 2yu plus 1. It is a quadratic equation in u, for which the quadratic formula is going to solve it. Okay. So according to the quadratic formula, my a is a 1, right? My b is negative 2y, and my c is a 1. Okay, so with that in mind, new page, new color, u is equal to the opposite of b. Well, b was what, negative 2y, so that would be a 2y, plus or minus, ooh, that's a problem, because it's not a function there, the square root of b squared. Negative 2y times negative 2y is what, 4y squared? Minus 4 times a times c, 4 times 1 times 1, so that's just a 4. All over 2a, which is just 2. So a little bit of looking at the graph and thinking about it is the plus is the right side of my hanging cable, and the minus is the left side. We have to pick one or the other. Tradition says pick the right side, which is what Desmos obviously does, because it gave us the upper half when we flipped it. Okay, so we're going to go with the plus, and we're going to skip the minus here, because otherwise it won't be a function. All right, let's clean this sucker up a little bit. Well, this right there factors, the 4 pops out. Square root of 4 is 2. So we have 2y plus twice the square root of y squared minus 1. All over 2, and those 2's divide out, don't they? And just a reminder, what was u again? U was e to the x. So I can just come down here and say, so at this point, e to the x is equal to y plus the square root of y squared minus 1. And just a couple of notes from the graph. Oops, wrong button. Oop, I need Desmos. Where are you, Desmos? And you can tease this out of playing with the e to the x's. Here we have a domain of all real numbers. I can plug anything I want for the red function, but the range is always going to be y is greater than or equal to 1. And if I have to just choose one side of this curve, like the right side, that means I'm modifying my domain to be x greater than or equal to 0. And when you do an inverse function, those get switched. Right? So we'll switch those in just a moment. So back here to the notes, my point is right here, I know that y has to be greater than or equal to 0 from looking at the curve. We're going to skip the algebra of that. It's not too bad. Oh, no, y is greater than or equal to 1. I don't know why I wrote 0 there. 1. So if that's the case, then my square root here is going to always have a positive interior. Y squared minus 1 will be greater than 0, and then this whole thing is positive. Why do I care about that? Well, e to the x is always positive. If it ever tries to be negative, then that means you have natural logs of negative numbers, and that means I is going to pop up. And we'd rather not work with I because it's hard to graph in 2 dimensions. We need like 4 dimensions, which is a little tricky on a board. So next thing, if e to the x equals that, then that means the natural log must be what x is equal to. So x is going to be the natural log of y plus the square root of y squared minus 1. Switching x with y, the last step in finding an inverse function, we've now finally calculated the inverse hyperbolic cosine. It is the natural log of x plus the square root of x squared minus 1, close. And although I can clean up the natural log of a product, I can't clean up the natural log of a sum. It doesn't do anything. I'm stuck with it. Okay, and a similar thing can be done with each of these. You can solve the hyperbolic sine equal to y and get its inverse. You can solve the hyperbolic tangent equal to y and get its inverse. And we could spend weeks on solving those algebraically. I'm more concerned about using them in calculus. So next thing we need to do is say, can we take the derivative of this sucker, for example? What's the derivative of the inverse hyperbolic cosine? So we're going to get some exercise in derivatives. So I'm going to rewrite that in its logarithmic form, which is the natural log of x plus the square root of x squared minus 1 in the root, close, close. All right, so here we have like the chain rule applied twice because we have a function within a function within a function. And there's a sum in there too. So we're gonna have to be very careful here. The chain rule says start with the outermost function. Outermost function is the natural log. Derivative of the natural log is 1 over. So I'm gonna get 1 over the interior, which is x plus the square root of x squared minus 1, times the derivative of the interior. Okay, the derivative of the interior there is 1 plus, and then I'm going to keep that in square root form. That would be 1 over twice the square root. And then when I take the derivative of that square root, I have to multiply that by the derivative of the inside. The derivative of x squared minus 1 is a 2x. So the 2x goes right there. All right, so that's what the chain rule tells us. Cleaning this up a wee bit, the 2's delightfully go away for us, right? They're going to divide out. And I think I should then deal with that addition right there. So to deal with that addition, just a side note here, just this part right here, ignoring the front fraction, I would rewrite that 1 as the square root of x squared minus 1 over the square root of x squared minus 1 plus x over the square root of x squared minus 1. So here's my 1, here's my other piece. Now I get a common denominator, so my numerator is the square root of x squared minus 1 plus x all over the square root of x squared minus 1. That's a square, believe it or not, there. All right, dot, dot, dot. That is still being multiplied by our 1 over x plus the square root of x squared minus 1. Does anybody see anything beautiful here? Yeah, Bang, bang. Look at all that canceling. We have a number, a big number divided by itself. This thing is the same as that. And so in the end, we finally get down to a relatively simple derivative, that the derivative of the inverse hyperbolic cosine is just 1 over the square root of x squared minus 1. Oof, that was exciting. All right, a similar procedure can be done to both find like the hyperbolic tangent inverse and its derivative. We're not quite ready for their antiderivatives. We need some techniques in chapter 8 to do those. So we're not going to get those yet. Let's try. Did that. I'm going to skip that one for now. Let's do something crazy from the homework. So the homework is a mixture of problems. Can you use the identities for hyperbolic sine and cosine? And there's a lot of similar identities. So I wrote down a couple. Where did I put it? Too many scribblings. Ah, there we go. So you can play around with the e to the x definitions and get a couple of things. Like we just showed a minute ago that the hyperbolic cosine squared minus the hyperbolic sine squared is 1. So that's like the Pythagorean identity for these guys. If you multiply the hyperbolic sine together by the hyperbolic cosine and you clean up the e to the x's, so if I take the cosh times the sinh, and I use the e to the x definitions, I'm going to skip all the algebra in between, if you don't mind for now. I'm going to get 1/2 times the sinh of 2x. Is that right? Yep, that's right. Which, if you think, hey, couldn't I put the 1/2 on the other side as a 2? Does this look familiar? It is the sine double angle formula. And I skipped the algebra in between, but just like we played with the Pythagorean identity earlier, you guys could pretty easily mess with e to the x's and come up with the same conclusion. It's about 4 lines of algebra to show that. And just about every trigonometric identity we know in trigonometry, there's a similar one, if not exactly the same, in hyperbolic trigonometry. Okay. The exceptions are we end up with a negative here instead of a plus, that the derivative of the cosh is the positive sign, not the negative sign hyperbolic. So there's a few minor differences. And the book has a table of all of those relationships. And so there's a couple homework problems where they just say, use these relationships and do some arithmetic or do some algebra. So I'll give you an example of one from the homework. So most of the homework is just getting used to these new definitions. I grabbed the wrong piece of paper. That's not it either. Oh, that's the one. So one of the homework problems said y is, this was number 9 in the homework? No, number 7 in the homework. So number 7 said let y equal the hyperbolic sine inverse. Is that right? Yeah. And then plug into it the cotangent, not the hyperbolic cotangent, but the cotangent from the old days. And it said find y prime. So you get to do this one tonight if you didn't already try it. Okay, so let's see. We need, I didn't derive it, so we need to look up the derivative of the hyperbolic trig function. So let's see. Didn't I have that on that cheat sheet I gave you guys? I think it was there. Let's go. Oops, did I forget to save this? Save modules, resources. It's probably in the resources page here. And where did that go? Derivative formulas. I think it's on this page. And for most normal individuals, it's impossible to memorize every formula in existence. And so pretty soon we're going to start looking up formulas when we need them instead of deriving or memorizing them. But What's that? There's too many to remember this time. Inverse trig derivatives. Okay. Oh, no, I want inverse hyperbolic. There it is. Wait on there. Okay. So we just found, where is the inverse cosh? Blow that up. Was 1 over the square root of x squared minus 1. X has to be greater than 1. That's the reverse of y had to be greater than 1 with the cosh. Now we need to do the sinh, and the only difference is a plus instead of a minus. Okay, we can do that. So back here, the derivative of the inverse hyperbolic sign says take 1 over the square root of the square of whatever was inside. Well, what was inside was the cotangent. So that means I'm gonna have a cotangent squared of x. And then a plus 1 is what that derivative formula said. Chain rule says you gotta multiply that by the derivative of the inside. What's the derivative of the cotangent? Tangent is secant squared, cotangent is negative cosecant squared. Yeah, in regular trig, they get negatives. In hyperbolic trig, the negatives don't necessarily come. So that's going to be a negative cosecant squared of x. All right, now, anytime I see a trigonometric function squared plus 1, I think, ooh, is this a Pythagorean identity? Okay, so sometimes I'm a little rusty on my cotangent versions of those, so I often look them up to be safe. So if we look up trig identities, which is one of the most popular Google searches for trig stuff in the world, we get 1 plus the cotangent squared is the cosecant squared. Ooh, that's nice because it's inside a square root. Okay, so now we have this is equal to 1 over the square root of the cosecant squared of x times the negative cosecant squared of x. And the square root of a square is equal to almost, not itself, the absolute value of itself, because the square on the inside loses track of whether it was positive or negative. So technically, this is 1 over the square root, the absolute value, sorry, of the cosecant of x. And then I'm going to write this, I'm going to put the negative out front, and I'm going to write, I wish that 1 wasn't there. Oh, well, I'm just going to write over it. I'm going to call this cosecant of x times cosecant. I can't write today. We'll just start that over. That's a mess. I'm going to write cosecant squared as cosecant times cosecant. Where are my tools? Back here. There you are. Okay, so absolute value bar, and then so this is cosecant of x times cosecant of x. All right, there we go. So the absolute value just controls the sign, S-I-G-N, right? And if I take a number divided by the absolute value itself, well, that's either positive 1 if they're both positive, or negative 1 if it's negative. Well, changing a sign based on something being positive or negative, that's what the absolute value does. So essentially, all of this can be rewritten as an opposite of the absolute value of the cosecant, because this pair just regulates whether it's positive or negative, depending on whether the original was positive or negative. It's a little tricky to work out, but if you throw a couple numbers in, you'll see, oh, right, okay, I get it. So I was able to reduce that. It's still hanging out. I can't get rid of that. This just oscillates between positive and negative depending on whether the numerator is positive or negative, which is what the absolute value does in the first place. Okay. Yeah, so that would be the answer there. So just pay close attention whether the H is in there or not, right? So that's the new thing we have to look out for, because we're going to see these a lot now. Just a side note. We struggled with integrals like 1 over the square root of x squared plus 1 before, because we didn't have an appropriate substitution to get rid of the stuff inside the square root. We now have a new trick up our sleeves. What's the derivative of the hyperbolic sine? It's that. So that means the fundamental theorem says an antiderivative for this sucker right here must be the sinh. And we get that pesky plus c. Yeah, so this is opening the door for taking antiderivatives that we couldn't take before. Okay, it's kind of exciting. All right, so let's do an integral related to these guys. There was a problem that looked particularly nasty in the homework, but once you break it down, it's not that bad. It was number 11 in the homework. Looked like this. The integral from the negative natural log of 12 to the negative natural log of 2. That's first when I started to freak out, but then I took a deep breath. And then I want 2 times e to the x times the hyperbolic cosine of x dx. Kosh. Oh, another slice of pizza. Okay, somehow I got to figure out how to ship pizza to Gerald. Oh, Domino's, right. We can send him a mini pizza. Okay. Classroom's no problem, but Gerald's like far away from us right now, as is Jared and Devin, and who else am I missing? I think those are my main ones. Oh, Caleb. Okay, so the trick here is to think, oh man, that multiplication, oh, that's a problem. But what is the cosh really equal to? Well, e to the x's. Oh, I just have a bunch of e to the x's here. So I can rewrite the cosh there as e to the x plus e to the negative x over 2. Now I'm just multiplying e to the x's together. So just some things that clean up. Here I have a 2 divided by 2. That's nice. And then I have an e to the x times an e to the x, which is going to be an e to the 2x. And then I have an e to the x times e to the negative x, which is 1. I love that. That's one of my favorite things to do with these. So really, I'm just integrating that. Oh, okay. This is a little better. And now the boundaries don't look so bad either, because if I give an exponential a logarithm to plug in, they're going to cancel each other. So this will simplify quite a bit. Not completely. Technically, I should put that in parentheses because of the sum, and this is with respect to x. Antiderivative here. Well, the derivative of e to the 2x would be 2e to the 2x. I'm missing that 2, so what do I have instead? A 1/2, right? So an antiderivative here would be 1/2 e to the 2x. And then antiderivative of 1 is just x. And then we have to evaluate that in the given boundaries. And that's where just a little bit of fun comes in. We played around with this idea last class. So new page. I'm going to get, let's go back to blue maybe, e to the 2 times the negative natural log of 12 plus the negative natural log of 12. Oh, no, wait, what was the upper bound? I'm sorry, 2. How are we doing on time? We gotta quit in 1 minute. All right, and then I'm gonna have a minus. I'm gonna put that in parentheses, e to the 2 times the negative natural log, there's the 12, minus or plus the negative natural log of 2. Ooh, lots of parentheses there. 12, good eyes, 12. That's worth a slice of pizza too. Okay, so if I switch the 2 and the natural log there, then I can rewrite this. So just let's focus on that guy for a sec. That would be e to the negative natural log of 2 squared from that 2 in front, right? Because power to a power means multiply them. We have another rule that says this negative right here can be brought in as a power of the base. So based on the rules we reminded ourselves of last time, this is e to the natural log of 2 to the negative 1. What's 2 to the negative 1? 1/2 squared. So that cleans up rather nicely. What happens to e to the natural log? They're inverses, they cancel each other. So this whole crazy thing right there happens to be 1/2 squared, or 1/4. Okay, so I'm going to have a 1/4 minus the natural log of 2. Here I'm going to have a minus. And similarly, what do you think that guy right there is going to be equal to? Instead of a 1/2 squared, it's probably going to be a 1/12 squared. Do the same process. That will be a 12 coming through. 1/12 squared is what, 1 over 144? So minus 1 over 144. And then I'm subtracting a negative there. So I'm going to have a plus natural log of 12. And I can't remember how far they wanted to clean this up in the homework. They wanted an exact answer. So I don't have time to finish this right now, but you would then have to take this difference. You'll get a number from that. And then there's a trick about these guys right there. So you'll figure out whatever 1/4 minus 1 over 144 is. And you all have magic calculators that do that. And then I'm going to have the natural log of, let's see, what was the order of those guys? Natural log of 12 is the positive one, minus the natural log of 2. And we have a rule about the difference of logarithms. That becomes the logarithm of the quotient. So natural log of 12 over 2 is just the natural log of 6. So it can clean up quite a bit. So we'll have some fraction. My recollection is that's 35. Okay, yeah. So 35 over 144. And that's about as far as I can take it, plus that. At this point, I would definitely be whipping out something like GeoGebra to double check that that worked out, because that was a lot of crazy stuff. Yep. Did I skip a 1/2 somewhere? Let's see, where are we? Oh my gosh, we left out the 1/2 there. Darn it. Okay. No, so the 1/2 lived with this guy right here. Thank you for catching that. I forgot about the 1/2 there, 1/2 there. And so there'll be a 1/2 with each of these guys just hanging out. And that doesn't change our numerator. So I think the numerator, that'll be then 35 over 288. Pretty sure. Because we'll have, yeah, because both of these will have a 1/2 times them. So I could essentially factor out that 1/2 from those two, so they have the same difference. Yeah, so it should be 35 over 288. Thank you. Plus the natural log of 6. All right, so your fun tonight is to just play around with the properties of the cosh and the sinh. Mostly you'll see a little bit of the tanh and some of the other ones. And then play around with some of their derivatives and integrals. And so you're going to spend a lot of time looking at the tables in the book. And the tables are, what are their identities? What are their derivatives? What are their integrals? The only integrals we don't have yet are integrals for the inverse functions. We'll get those in chapter 8. Okay? All right, have a good day, do good math. And if you didn't get me your take-home test, I need that today, please.
Hey, do you have the password for the homework?
It is, please get it done now. Please get it done now. All one phrase, no space, no capitals.
Great, thank you.
Yep, have fun. All right.